Okay, today we're going to be learning the famous Dijkstra's algorithm. Dijkstra's algorithm is an algorithm that gives the absolute perfect shortest path from one node to another in a weighted connected graph. By shortest path, um, I mean the one with the least expense. Now, if your graph is not weighted, the shortest path we've already done. The shortest path is simply found by doing a depth, excuse me, a breadth first search would be easy to do. You could also do a Dijkstra's algorithm as well. Just put all the weights as one. There are some algorithms that are known to be faster. There's a modified Dijkstra's. There's a something called A star. They're slightly faster, but Dijkstra's is just a classic, and it's an algorithm that most sites will tell you if you're going for a job interview, for be a programmer in computer science, go in there knowing this algorithm, and it's just beautifully simple. So here we go. Our goal is to find the shortest distance from, let's say, A to C. But Dijkstra's is going to do better than that. Dijkstra's is actually going to tell us the shortest distance from A to every single node. So we're going to go from, our goal was to go from A to C. What's the shortest distance? Well, we can do that, and we're actually going to answer the shortest distance to A, B, C, and D. So here's what we do. We're going to start at A, and this is us. And we're going to look at all of these different tickets we could buy. Imagine these are we're at a train station at a depot, and we've got all these different tickets we could buy. So I see that this distance of 2 is the least expensive one I can be. So I'm not going to take that route. I'm going to phone a friend. I'm going to send a representative out on this train to D, and they're carrying with them the cost of 2. And now we're going to get on the radio together. We're going to say, hey, what's the cost to get where can you get to? And my friend over here at D is going to say, well, I can go back to station A, but you already know that. But I can go to station C. And I said, well, what's the cost to get to station C? He says, well, it only cost me $4. And I'm like, oh man, my C is $5. He goes, yeah, but don't forget, if you're going to come my way, it cost you 2 to get here, so that's 6. So I say, you know what? Let me write this down. So I've got a distance to B, C, and D. My distance to B is 2. My distance to C is 5. My distance to B is 3. My distance to C is 5. My distance to D is 2. My friend here says, hey, I can get you to C at only a cost of 4, but you got to come here first. And I said, no, because that cost me 2. That's too expensive. So I'm not going to do that. So what I do next, I go, all right, let me see what's next on my list here. I have, if I look at my costs, I can go to B for 3. I can go to C for 5 and go D for 2. I've already been there. I don't want to go there again. I'm going to go over here to B. So I'm going to send my friend over here. And we'll put this one in a skirt. And my friend at B says, hey, I can buy you a ticket to C. And I said, how much is it? Well, it only costs $1. But don't forget, it costs you 3 to get here. And I say, wow, because we were on the phone here, right? And I said, wow, that means $4. And I look and see, well, my cost list right here is 5. I'm going to cross that out and make it 4. And then we're done. And now what I'm going to do is I'm going to send out another representative and say, hey, would you go to C? And and I'm going to tell them, hey, go from A to B to C, though. All right, so then I got another relative over here, or a friend, or whatever, and they're over there, and it cost them 4 to get here. Now, I stopped the graph here, but you can imagine there might be more things that they could go and look at, right? And we just continue this process of, I picture sending out feelers, like little tendrils, little sensors, and I'm just sending them out. And I'm constantly updating my array of cost to get it cheaper and cheaper and cheaper. By the time you visited all the nodes, this is guaranteed to be a list of the cheapest nodes. Okie dokie. So that is all. Let's go ahead and code it up. So I've just got this same, project I've been working in. Let's make a new class here, and I'll call it Dijkstra. 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 All right, you with me still? All right, I'm going to import java.util. Do I need any? Actually, I'm trying to think what all I need, if anything. Yeah, I don't really think I need anything, frankly. If I do, I'll come back up and import it. All right, we're going to have an adjacency matrix because we know that's how we make a graph. And I'll just make my constructor take in an adjacency matrix and initialize ours with it. All right. So there's lots of different ways you could do this. We could write the method to return the minimum cost. We could write the method to calculate and fill in that minimum cost array from a starting position. We could do that. And then just return specific items in that array as needed. What I'd like to do today is I would just like to return the entire minimum cost array given a specific start node. Then the user can do whatever they want to do with that, or we could write another helper method. So we're going to be returning an array of costs. And we need a start node. And we could make this problem perhaps more useful by making it to where we actually tell what path to take and all that stuff. And we might look at that later. But right now, I just want to keep it real simple. We're just solving for the minimum cost, shortest distance array. I'm going to go ahead and make an infinity. Let's see if we can say private int, private static int infinity, and I'll just make it equal to like 1 million. Just some big. Anyway, I'll make it public. Why not? Public static final. There we go. Yeah, that way people can see my constant and my documentation and whatnot. So first thing we need to do is create our 2 arrays that are going to help us do this. We need to have a visited array. I think we've seen that like a million times, right? Boolean visited equals new Boolean array, and by default these will all be false upon creation. Remember, the adjacency matrix is a square matrix, so I can just get the number of rows, and that's the number of nodes that I have. Oh, I'm missing my... There we go. And we're also going to make an array for minimum cost. I'll call it cost table. How's that sound? And again, it's just it's the length to all the different nodes. So visited our start node, we've already visited, so that's going to be true. The cost to get from our start node to our start node is 0. But everything else is going to be infinity. So actually, I think I'm going to fill this matrix with infinity, and then I will put 0 for my start node afterwards. So I'll say for int I equals 0, I less than cost table dot length I plus plus. Cost table bracket I equals infinity. So I'm going to start assuming that it's impossible to reach any node, and then, then we'll update it from there. I mean, obviously, if I'm connected to any node at all, that cost should come down, but we just need a starting point. And I'll make the start node 0. All right, there's lots of different ways I can stop my loop, but I think I will just make a variable called nodes visited. And while the nodes visited is less than the number of nodes that I have, we'll keep looping. All right, so we're going to write a while loop. So with this, I say, while the nodes that I visited, I haven't visited every node in the graph. Once I visit every node, the graph will be done. First thing I'm going to do is I'm going to get a node. And so we're going to need a method called getNextNode. That'll make it easier. So I'm just going to, we're going to write this to do. Increase the number of nodes that I visited. Set that to true. And what getNextNode does is simply going to find the next node that we should visit. Remember, it's the least expensive node. Okay, now I was wondering if I needed to do this, and I do. I went through and I set everything to infinity. Before I can enter this while loop, though, I thought maybe I could update it in the while loop, but I need to do it first. So I set everything to infinity. I think I could just instead, let me think for a second. I'm going to say adjmat bracket start node bracket I. So instead of starting it all at infinity, I am going to start everything at the value in the adjacency matrix, and we'll have infinity. Whenever there's not a connection, this will be infinity. But we are going to then write over it because typically the adjacency matrix from a node to itself is infinity unless there's like a loop. So we'll write over that, making it 0. Okay, yeah, I like that better. Okay, so now what we're going to do is we're going to loop through our adjacency matrix, all of our nodes. And I could say cost table.length, adjmat.length, whatever. They're all the same. They're all just the number of nodes. If the adjmat bracket my current node bracket I plus the cost to get to I, which is cost table bracket let me make sure that we understand what we're saying here. So what we're going to do is we're going to see if, so we saw when we updated our cost, when we went to C, it was less. So if the cost, so right now our current node is B. If the cost to go from B to C plus the cost to get to B is less than the current cost to C, we're going to replace it. So that's what I'm saying. If the adjacency matrix just tells me the cost to get from my current node to node I, if I take the cost to go from my current node to node I plus the cost table, which is the current lowest cost to get to current, if that is less than what is currently stored at I in my cost table, then I'm going to change my cost table to be that. This is kind of an old style of doing this. It would probably be faster to use math.min. So I'm just going to make that alternatively. Here's an alternative way of doing that. You could say cost table bracket I. You could say cost table bracket I is equal to math.min of this and the current cost table. So that's how that works. So I think I'll erase the if statement and go with that kind of high functioning version, if that's okay. So for each place in my cost table, I'm going to set it to either with the lower of the two, either what's currently there or the cost to get to the node that I'm currently at plus the cost to get from the node I'm currently at to I. So again, current would be like what my current node is B. I'm going to see if the cost to get to B, which would be the shortest path to B, plus the cost to get from B to C is less than what is currently the cost to get to C. If it is, that becomes my new value. And basically, that is it. Then when we're done, we simply return the cost table, because that's what we promised to return. And then the user can figure that out themselves, or we could write a little helper method that does it. We do need to. I think it works best to put the logic for get next node though into its own little method. So what do we need to send it? The visited array, and I think that's it. So we already got the adjacency matrix. So our goal for get next node is to simply find the cheapest node. So I'll say public int get next node, and it's taking in an array of visited. So I need to figure out which node have I not visited and has the shortest cost to get there. So what I'm going to do is just make a couple of variables. I'll say best node. I'll start it at -1. I'll say least cost, and I'll make it infinity. I'll say for int I equals 0, I less than... oh, I need the cost table too. Dang it. Let's send it the cost table. So yeah, I need that as well. I less than cost table dot length I plus plus. If the cost table bracket I is less than the least cost, and I haven't visited I, then best node becomes I, and least cost becomes cost table bracket I. And then we just simply return best node. So, and there, maybe I didn't need to write a least cost. I could have just accessed the table at I or at best node, but I thought to make two different variables. So whenever we find an I that has a cost to get to it that's less than the other one, then we do it. So, but just understand the logic of it. Get next node is simply finding the next node that we should return. The next node we should visit, which should be the least expensive node to travel to that you haven't already visited. And I think that's it. Let's do a little tester. All right. Let's make a matrix. I don't remember what this graph would look like. Well, maybe we should draw it out. But I think it's connected. And we'll make a Dijkstra object. And I'll get a cost. cost table CT. D dot, what is it called? Like run Dijkstra? Run Dijkstra. And we'll give it the starting node of 0. And that should print out the cost to get to each of the minimum cost to get to each of the other nodes. And according to this, it's 06511.3. I think in order to believe that, I think I should probably test it, though. See if I can't draw this out. So let's see here. We have, how many nodes we got here? 1, 2, 3, 4, 5, right? This is 0, 1, 2, 3, and 4. So the cost from 0 to 1 is 7, 0 to 2 is 8, and then 0 to 4 is 3. The 1 is connected to 0, it's connected to 2 at a cost of 1, and nothing else. 2 is connected to 0, it's connected to 1, it's connected to 3 at a cost of 6, and it's connected to 4 at a cost of 2. And let's see here. 3 is connected to just 2, and 4 is connected to 0 and 2, and that's it. All right, so just doing a quick, this is not a complicated graph, so we could probably just look at it and see what we think the result should be. From node 0, I see that I could get to node 2. Obviously, it's 0 to get to 0. Node 1, I think we can get to node 1 in 6. Do you agree? If I go this way, 3, 2, 1, I think I can get to node 2 in 5. I can get to node 3 in... So to get to node 3, if I go to node 2, that's 5, plus 6 is 11, and node 4 is 3. And the results of our running Dijkstra is 06511.3. I feel very happy with our results. All right, and that is all for Dijkstras.